Hopefully this is the last technical interruption. But again, thank you so much for being here. This is my PhD defense. I'm Prashant Kodali. I'm advised by Professor PK and Professor Manish. And the title of this thesis is sort of pun at the phenomena that we explore in this thesis. It's called Computationally Code Mixing or Challenging It, where we try to improve the generation analysis capabilities in code mix settings. Okay. Right. At the outset, let me thank the evaluation committee for the very useful and very insightful comments on my thesis. Professor Mayank Singh, Professor Sandeepan, and Professor Radhika for taking the time and reading through the thesis, and also the advisors, Professor PK and Professor Manish, for shaping this, helping me shape this thesis. So this is the outline for the next 45 odd minutes, where we'll spend some time on the background. What is code mixing? What are its real world applications? And what are some of the challenges that we have identified and tried to work with? And I will briefly follow it with some research statement as to how we have tried to fill up those gaps. And then we'll dig into each of those components in the thesis. Finally, we'll end with some limitations and future work that we have envisioned in this thesis. And yeah, that will probably be the end of the presentation. Right. Jumping into the preliminaries, at the outset, I think we should clearly define what code mixing is. Code mixing, generally in linguistic literature, has been defined as this juxtaposition of linguistic units from two or more languages. These could be words, these could be morphemes, or these could be larger linguistic units as well. As a phenomena itself, code mixing is a spectrum where the switching could happen within the sentence level, where in the first example, you can see that the colors are, by the way, indicating the language of the token, and you can alternate, a speaker can alternate between multiple languages within a span of a sentence. Another example of it is intersentential mixing, where the speaker switches between languages at a sentence boundary. So you speak one sentence in Hindi and probably the next sentence in English. Then there are very interesting kinds of switching that you see in agglutinative languages, like the examples that are there on your screen are English, Telugu, and English Malayalam. And the example of interest is these words where EMI, which is an English word, is appended with a Telugu suffix lu. Right? And same is the example with the Malayalam example of shopping, followed by a suffix nu. So here, these are another kind of mixing where the mixing is happening more at a word level itself. So having understood what code mixing is, it's very also important to understand how have linguists looked at code mixing. What are the theories that have been proposed to explain how code mix sentences are generated by humans. I find this abstraction by Metson and et al. Very easy to, as a way to understand the grammatical theories of code mixing. Throughout the linguistic inquiry into code mixing, there have been multiple theories that have been defined, that have been proposed. And these authors here break it into multiple categories. One is alternation, where you are alternating between linguistic units of different languages. Then there is alternation, which is where you complete one turn in one language and then switch to another turn. And there is, over a period of time, because of some shared grammatical or other structures, these patterns are much more intermingled. But irrespective of what the theories have been, there have been always edge cases as to where these theories do not apply, or there are cases where these theories break down while justifying a code mix sentence. Beyond the linguistic understanding of what code mixing is, it's also very important to understand where and why does code mixing happen, because that is where you can justify or understand where is the utility of such an inquiry. Code mixing has been used a lot in social media networks, and that is probably the genesis of this thesis, where people are expressing a lot of opinion on social media platforms, let it be political commentary or product reviews, any such thing. And another very important use case is you pick up your favorite IM chatting app, and you, more often than not, if you are bilingual, you might have code mix in your chat history. Another very important example of why code mixing happens is just this filling some lexical gaps. So the example that is there on your screen is basically a bilingual 2-year-old, not even bilingual, trilingual 2-year-old who's trying to mix Telugu, English, and Hindi in her case. And she was trying to mix words from different languages just to form a sentence. Code mixing also has been used as a device to express, let's say, satire. The example that is there on your right of the screen is an example where a poet in the pre-independence era is trying to pass on a satire on some of the British laws that are there. Or you can think about ad campaigns that are run by companies like Airtel. If you're old enough, you would remember "Har ek friend zaruri hota hai," and which is a way to appeal to the younger demographic. Right. Coming to the real world applications of it, there are studies of late which have tried to quantify as to what is the rise or what is a portion of code mixing in social media platforms. And this is an example. The graph on the left is an example of looking into how code mixing in English Hindi has evolved over the years, right? And the studies essentially make a point that the quantum of such text is growing over the years. So especially if you're a social media company and you are having to moderate user generated content, let it be for hate, let it be for mining some user opinion, you need to take care of such phenomena because it is a substantial part of social media ecosystem. Another use case that is sort of logical is that an example that you see on the screen where I basically have to guide certain students to a certain exam center, right? And I have to say that your ID card will be verified. Now, very proper Hindi way to say this, Shuddh Hindi way to say this is परीक्षा केंद्र पर आपका पहचान पत्र सत्यापित किया जाएगा, right? And an alternative way to say this is that exam center पर आपका ID card verify किया जाएगा. Now, depending on who you're talking to, depending on whether they are bilingual, whether they're proficient in Hindi or they're proficient in English and Hindi, it's up to the user, like what would they prefer. And I think there is value in presenting both to a user. Right. So, yeah. When we set out to work in this area, these are some of the primary challenges that we had identified, and these have also grown along with the thesis. With the first bucket that we identified was just these metrics to assess or grade a code mix sentence, right? When you're saying this sentence is code mix, now there is going to be nuance to it, right? What is the degree of code mixing, or what is the signature of that code mixing? What kind of code mixing, right? To answer such questions, you need to rely on metrics, right? Which give you quantitative measures to convey that point. Another central tenet to this thesis is overcoming the data scarcity. Coming to any Indian languages, and more so in situations where you are mixing two languages, your traditional sources of code mix data are very limited, right? You can't expect to find a lot of code mix data in sources like Wikipedia or news, right? So what are your alternative ways? If you are relying on synthetic data generation, then then how do you ensure that whatever data, synthetically generated or not, is of good quality? A third pillar of this thesis is if you have multilingual models which are proficient in, let's say, English and Hindi, but are they proficient in English-Hindi code mixing, right? If not, what are the model adaptation strategies that you can adapt or you can evaluate to start with? During this PhD journey, one more thing that was very apparent was just the lack of any standardized pipelines or toolkits that you can apply so that you can start experimenting quickly. There is a huge entry barrier in terms of where these data resources or model resources are, and there is substantial effort to bring them into a single usable toolkit. So, having identified these research gaps, the overall research statement that the thesis tries to achieve is basically to overcome data scarcity by looking at quality controlled synthetic data. Also, while providing necessary analysis and evaluation toolkits, whether they are data sets or metrics. The third thing that we evaluate is model adaptation and understanding just how well we can fine tune multilingual models for a certain code mix task. And finally, we also have this goal of bringing all of these resources under one single umbrella, where any researcher or any user for that matter can actually hit the ground running without a lot of effort if they are interested in code mixing research. So these are some of the contributions that we have categorized bucket wise. We will get into each one of them now. So starting with the first one, the first attempt that was made in this thesis was trying to come up with these metrics which are useful while looking at code mix sentences, whether it was to create or whether it was to understand what is the signature of code mixing. So that brings me to the first part of the first contribution of this thesis, which is called SymCom. It is a syntactic view. It is a metric that is grounded in syntactic nature of code mixing. This paper was accepted at findings of ACL 2022. Yeah. So code prior to when we started working in this on this problem, there have been many metrics that have been existing, proposed by previous researchers or otherwise, which were essentially trying to identify or answer this question: what is the degree of code mixing? Essentially trying to answer this question: how code mixed or not code mixed the sentences. So a logical thing to do there is basically to look at what are the token-wise language IDs, right? So in the two examples that are there on your screen, these are again English Hindi code mix sentences. The colors are again indicating which language is that token coming from, English or Hindi. If you look at, forget the tokens, what is the semantic content they're carrying. If you look at just the token distribution, the language-wise distribution of the tokens, you can see that there are two Hindi tokens followed by two English and followed by three. And this pattern is same across both the sentences. So the metrics that rely on looking at such a distribution of these token-wise language IDs, you can compute them into simple metrics. The simplest thing that you can do is take a ratio of English words to a Hindi word, or vice versa. If you were to apply these kind of metrics, which just look at the language ID, the quantitative measure to that is the same, right? It essentially says that that number 28.7 is saying that this is how code mix the sentences, right? Across both these sentences, it's the same. But looking at it a bit more closely, there is some nuance to it, right? There is in example one, what is switched? What are the nature of the tokens that are being switched, as opposed to sentence two, what is the nature of these tokens? So the simplest thing that we did there was in example one, what is being switched is a verb and an adposition, whereas in example two, what is being switched is a noun, right? The window shopping is basic. English is bringing in two nouns to the sentence. So the insight in this work was basically to, when you are quantifying this signature of code mixing, not just look at the language ID, but also take into account the syntactic nature of that word. And the syntactic nature that we could compute easily was the pause tag. One of the simplest things that we can do was the pause tag. So by looking at the language ID and the pause tag of those words together, we propose this family of metrics called SymCom, which can be computed at a syntactic unit level. By syntactic unit, I mean a pause tag level, right? You can compute a SymCom for a noun, SymCom for a verb, etc., all the 13 pause tags that are there in universal dependency tag list. You can aggregate this at a sentence level, and further you can aggregate that at a corpus level. To give a better understanding of what this metric would mean, this metric can take a value from +1 to -1, SymCom for a syntactic unit. The extremities +1 or -1 indicate a language, right? If a SymCom score is +1, that means that that syntactic unit, for example, nouns are only contributed by that language. But if a score is somewhere in between, that means that there is a mixture, right? Nouns are being mixed, are coming from either from both English and Hindi, or language 1 and language 2. So when you apply this metric at the example, the running example that we have, you can see that in example 1, nouns are solely coming from Hindi and verbs are solely coming from English, right? And the scores are indicating that. SimCom noun is -1 and SimCom verb is +1, right? Extremities, no mixing. Whereas when you come look at example 2, you can see that SimCom for noun is neither +1 nor -1, but somewhere in between, which means that both English and Hindi has contributed words of that pause tag, and verb still comes only from Hindi, so that maintains its score 1. So when we compare these metrics, SimCom, with metrics like CMI, you can see the contrast as to what kind of insight is SimCom bringing into the picture. But a necessity for us to compute this metric is having a reliable pause tagger, right? Which is not necessarily a given in code mix settings. So the first thing that we tried to do was to train a pause tagger that is good at, or not perfect, but rather at least to a certain extent is good at computing pause tags in English in the code mix sentences. So we use existing English in the universal dependency tag data to train a pause tagger, and this was the overall performance. But looking beyond a single accuracy measure of 92.75, this is directly correlated to how much of a particular pause tag was present in that data. So our pause tagger that we trained was not very good at, let's say, identifying interjunctions for that matter, right? Because they formed a very small portion of the data. So what I'm trying to say is that when you're looking at SimCom and whatever insights that you're drawing from it, it is very much contingent on the efficiency of pause tagger and across different pause tags. So now, okay, we have a metric now, and you have basically a necessary components for you to compute such a metric. But what is the utility of it? So first thing that that it allows us to ask is look at how are open class words distributed as opposed to closed class words. Now this question is very important because this is what grammatical theories have long told, right? Grammatical theories of code mixing have long told that open class words are more likely to be switched, right? So now here is a quantitative proof or justification or backing to that same argument. Another insight that you can get from such an analysis is that what kind of pause tags are switched together, right? Again, this is an important insight because it can help you identify sentences which are probably not so natural. If a verb switching with a noun is less likely, then those kind of patterns we would probably be able to find based on these tools and these analysis. Another thing that we did was compute these SimCom scores across corpuses and try to compare these data sets just to identify if there is homogeny or there is any difference in the different data sets that are out there. And the key takeaway from this kind of analysis is only that you have a means of computing signature of code mixing and trying to compare across data sets. So in conclusion, SimCom is basically a metric that is syntax aware, and it tries to quantify what kind of at what level the syntactic mixing has happened. And our analysis also has given, let's say, quantitative proofs to this argument that in matrix language theory, closed class words are less likely to be switched. Of course, this study has some limitations. For example, to extend SimCom as a measure to languages beyond English Hindi, a very basic requirement is a pause tagger, which is not a given for many languages. And extending this to mixes, the code mix settings where there are more than two languages being mixed, like English, Hindi, Bengali, these metrics would have to be modified to suit such situations. That brings me to the end of the first component of this thesis. I'll probably take a minute to see if there are any clarifications that I can provide.
post markers, they can be code mixed or switched at that point.
Right.
So those come under closed class.
Yes, but I don't think that theories essentially say that closed class class of words are not mixed at all, but their degree is much lesser. So when I'm trying to code mix, the kind of mixes where I'm trying to borrow English words, English nouns for that matter, मैं movie देखने जा रहा हूँ, is more likely to be the case than switching other. But yeah, so one of the very interesting examples that we see was, I'm very happy. Yeah, I'm happy ki, you are able to defend the thesis, right? So that key is basically the phenomena that you're talking about. And these connectors are also very useful for us to mine data. So we had identified trigrams or fourgrams which are centered around key, but, and stuff like that. But yeah. But I think the key takeaway was that although that mixing is there, but it is less common than noun switches or verb switches or adverb switches. Right. So I think we can get into the next component of this talk, where we looked at there are two goals with this next part of the thesis. One was to understand how acceptability of code mix sentence happens, and second thing, also use this as a device to curate data that you can then use to train models or adapt models. So this work is basically revolves around understanding acceptability of code mix sentences. This was accepted at ACM transactions for low resource language information processing, TALIP. But yeah, to begin with, I'll probably rely on these sentences to motivate the phenomenon. The four sentences that are on your screen. Sentence one is a purely English sentence. I conduct research on code mixing. Example 2, 3, and 4 are code mix versions of saying that. So example 2, when I read it, मैं code mixing पर research करता हूँ. To a English Hindi bilingual like me, it seems natural, free flowing, fluent. The third example is I do शोध कार्य on code mixing. शोध कार्य is the Hindi equivalent of research, but to me it doesn't seem so fluent. It seems rather forced. Somebody had put a gun in my head and asked me to code mix. This is what I would come up with probably. And the fourth example, मैं conduct code mixing, research code mixing per, right? This is again probably a 2-year-old trying to form a sentence, right? But if you were to present this to English in the bilingual, any of these sentences for that matter, 2, 3, and 4, how would they perceive it? How would they rate it? What is acceptable to them? What is not acceptable to them? This is an important question to ask because at the end of the day, what are your data sets made up of? Code mix data sets, when you're talking about it, what are they made up of? Are they made up of examples like sentence number 2 or 3 or 4? It is intuitive to say that it is better to have code mix data sets which are more like 2, less like 4. And that is what we wanted to understand and analyze in this work. When we discussed code mix metrics in the previous part of this talk, we were motivating it by saying that these metrics are trying to capture a signature of code mixing. They quantify what is the signature of code mixing. But are they sufficient for you to distinguish between example number 2 and 4? Okay? That is an important question because that can inform how you curate your data sets, how you collect your data sets. So to ask this question or to even analyze this question, you need to have certain amount of data, which is basically a collection of such human judgments, right? Human judgments in the sense whether example number 2 is fluent or example number 3 is fluent. So we had a large scale data collection exercise where we looked at 2 data sources. One was synthetically generated data, and second was data that we could source from social media platforms. So there was a reason for this dual approach because synthetically generated data is bound to give you a good distribution across the whole spectrum. The spectrum being perfectly acceptable, not at all acceptable, right? Synthetically generated data, you can assume that it can give you a good distribution across the spectrum. Whereas on social media platforms, it is human generated, well and good, but you are less likely to see examples like 4 in social media platform, because it is human generated. They would have not written it like gibberish. Say, I mean, not a safe assumption for social media platforms, but one that we would we would go with. So for synthetically generated data, we relied on this toolkit called GCM toolkit, which is grounded in grammatical theories of code mixing. And given an English Hindi parallel sentence, it will give you some alternatives, code mix alternatives for that sentence. Another thing that we did for social media platform, the data collection was not so trivial. We were querying Twitter API in this case with n grams, ranging from 2 grams to 4 grams, which were mixed in this nature. And as Madam had pointed out a while back, I am happy key, right? So this is a mix. This is a trigram. There is some mixture, right? Two tokens in English, and the key token is coming from Hindi, right? So we identified trigrams, bigrams, and 4 grams like this, and use that to query Twitter APIs. And so any sentence or any tweet for that matter, which contains this trigram or bigram would be part of the data set. And we used snowball sampling because we started with a very small seed, but we iteratively identified more n grams and used them to query further and accumulate the data. To overcome this challenge of no negative samples, social media data will not have a lot of negative samples, will not have a lot of bad samples. To create these negative samples, we relied on certain perturbations where we randomly swap tokens, we randomly delete tokens, and we also do some back translation where we pick a segment of tokens, translate it to language from L1 to L2 and then back to L1. So this would introduce the noise and probably some negative samples. This was followed by taking a sample and asking annotators to rate it. Because this is also a subjective call, what would be acceptable to me might not be acceptable to the second person. So there is certain subjectivity involved in this. To capture this nuance, we had each sample annotated by three annotators. So this divergence or agreement or disagreement between these annotators was also a very crucial signal to capture. So this is a sample UI that we used to get the sentence annotated, where a sample was presented to an annotator, and they had to pick one of these 5 options. One being definitely unacceptable, and 5 being perfectly acceptable. And since we were dealing with social media data, we wanted to rule out any abusive text or non-English Hindi text, non-code mix text. So there was options for annotators to deal with it as well. This was the overall composition of the data set. A large portion, almost twice that of social media data, is coming from synthetically generated data. And there is also a good distribution of where, to what degree did the annotators agree or disagree. To rule out any noise, annotation noise in the data set, we removed any samples where the disagreement was more than 4. And also an interesting insight here was our annotators took much longer to annotate a social media sample. The 2 reasons that we could attribute it to was, one was longer spans, longer text in social media platforms, and also because of misspellings, because of social media noise like user mentions, hashtags, etc., etc. It was slightly harder for annotators to read and arrive at an annotation quickly. So the first key result in this analysis was to ask this question whether code mix metrics are well correlated or not correlated, or what is the degree of this agreement between code mix metrics and acceptability judgments. So looking at what is there on the screen is on the left side, these are correlation figures. So bounded between +1 and -1. What we found out was that none of these code mixing metrics were correlating well with acceptability judgments. The only thing that probably came close was number of switch points, or average number of switch points in a sentence. Having looked at this correlation analysis, we also looked at maybe a linear combination of these metrics might give you a better handle at predicting acceptability. These are the linear regression coefficients, but the explained variance that was there out of this linear regression was very, very low. So the key outcome here, or the key takeaway here was that code mixing metrics on their own are probably bad predictors of acceptability. So the next thing that we did, easiest thing that we could do again, was see if we can fine tune a multilingual model ranging from an encoder model or a decoder model to and see if by fine tuning on our data, can it actually give you a fair amount of prediction accuracy. So in our experiments, what we found out was that fine tuning even a smaller decoder model gives you the highest, much better than encoder model. And this was, and we compared this with simple prompting to GPT 3.5 at that time. We compared it with both 0-shot and 5-shot inference, and we found out that the performance of specifically fine-tuned model, which had a benefit of looking at 16,000 samples, was much better than a 0 or few-shot prompting of large LLMs. One more interesting thing, again, something the previous studies have also noted, is the difference in performance when the text is romanized as opposed to the text being normalized. By normalized, what I mean is the Hindi tokens are converted to their Devanagari form. Typically, when a code mix sentence is written, both English and Hindi are written in Roman script. But when we talk about normalized form, the Hindi tokens are converted back into their Devanagari form. And models are, again, the previous literature as well as our experiments have shown that models are more comfortable when the text is normalized. We tried to understand why this happens. We looked at two things. One was tokenizer fertility and perplexity of the models. We see that code mix sentences where the Hindi tokens are in Devanagari form are broken into much fewer tokens, right? Subword tokens. And that was one thing that we analyzed, and this was consistent across models. And perplexity wise as well, models these numbers indicate that they were much more comfortable, they were generally comfortable with the normalized form as opposed to the romanized form. So I'm on the same slide. There's slight delay, but I think that is so. Yeah, so perplexity is generally higher for sentences being in Roman form. One conjecture that we have is that it is probably because model would have seen Hindi more so in the Devanagari form than in Roman form, because typical sources like Wikipedia or news articles, the Hindi would be in Devanagari form. Beyond the simple RMSE or the MSE scores that we looked at in the previous slide, we also try to understand where the errors are. And the models generally had a tendency, both the Llama models and the XLMR models had a tendency to overpredict, have a positive bias in the sense they would overestimate the acceptability of a sentence. And they would struggle with sentences where the acceptability, generally the average acceptability score was less. We again try to understand if there is if those errors in predictions correlate well at all with the code mixing metrics, but the correlations were minimal if at all. So in conclusion, the outcome of this study was a data set that we called CLIMB, which is a very large scale data set comprising of 16,000 samples, each sample being annotated by three annotators. A key takeaway from this study was that code mixing metrics are not sufficient when you're curating your data sets. You need to look beyond. And generally fine-tuning even a smaller model like XLMR or a Llama small 1 billion or 3 billion model would give you competitive performance. There are certain limitations for this study. One is that curating such a data resource for one language is sufficiently hard enough, but to expand this to other language pairs is all the more harder. And general tenets of acceptability in code mixing will probably emerge once you do this at more language pairs or expand the coverage. Another point to remember here is that our annotator pool had a significant bias in terms of who the annotators were. Our annotators were university students who are coming from north of India. Their mother tongue is Hindi, and I mean age group is 19 to 23. This, of course, would not probably generalize if you go beyond go to different demographics, whether in terms of geography or age. So that is something that should be remembered while interpreting these results. I think I'm running a bit slow, but I'll try to speed it up. So the next, next contribution of this thesis was again in the bucket of overcoming the data scarcity. And here we contribute a data set, which is a task-oriented dialogue data set in Hindi and also in English Hindi. This was accepted. This is a collaboration between multiple universities. We contributed the Hindi and the English Hindi data set. This was accepted at ACL 2023. So why this task? Why this task is worthy of creating a data set? Generally in code, if you look at code mixing evaluation landscape, everything is, there are two kinds of biases. One is that it is very sentence classification heavy. All the data sets are of that nature, or token classification heavy. There are not data sets which go beyond these levels. And another thing is, if you think about where code mixing is, where code mixing has utility, computational tools to code mixing has utility, it is where you can interface with users who are talking like you were talking in code mix manner. However, to evaluate a language model's proficiency at being good at certain code mix dialogue actions, there was no data set for us to evaluate, and that is where this study is originating from. And also there is some literature, previous literature that I have pointed out here, which essentially said that multilingual speakers prefer chatbots which code mix, and more specifically who code mix like they do, right? So that is a larger motivation as to why we took this route or went down this route. So the outcome of this this whole exercise was this multi-turn task-oriented dialogue dataset, which spans multiple domains. There are 12 domains here. By domains, I mean restaurant, weather, train booking, etc., etc. And there are multiple turns within the dialogue. And we created 3 sets essentially through our data annotation exercise: a few short setting and some sets, and similarly sized set for validation and test. And these were created for both Hindi and English Hindi. The key challenge in this whole exercise was, let me skip a slide ahead and show you what was how were the annotations carried out. So here is a UI where which was given to the annotators. They have a source English sentence to which they are either trying to create a Hindi sentence or a code mix English Hindi sentence. So the whole annotation exercise was centered around this approach, where an annotator is not asked to write the sentence ground up, but rather is presented with an alternative which they are supposed to correct if at all it is not fluent. In addition to that, they also have to mark the corresponding entities. So if the English sentence is talking about a certain restaurant or a place, then its Hindi or its English Hindi translation should also have that entity, and there should be some correspondence, because that is what is useful for your downstream task evaluation. So the key challenge in this whole study was, how do you come up with these alternatives? For Hindi, yes, you can rely on translators, but for English Hindi sentences, what do you do? So again, we went back and we leveraged this toolkit called GCM toolkit, which would expect an English and a Hindi parallel sentence, and it will generate some candidates for you. But there are some cases which we found out around 40% of the cases where GCM does not produce an alternative. It either errors out or it does not give any alternative. In such cases, what we did was we had some manual rules to switch tokens. For example, we would have rules to switch nouns and adjectives, or just switch adjectives. And again, the humans would post-edit it and correct it. Having created this data set, it was also important to benchmark as to what today's models are. Where are they standing in terms of such a task? So the key takeaways looking at these results is that English, as expected, outperforms both in Hindi and English Hindi. both in zero shot settings and few shot settings. The gap is slightly improved when you go to few shot settings. Models generally get better at English in the settings when they have seen a few examples, but still the gap remains more or less high. This was again a model that was trained. The base model that was trained in those previous results was an MBART model, encoder decoder model. But when you extend this to larger models as well, I'm referring to a study not done by us, but a different lab using our data sets. We can still see that even for models like GPT or Palm, the difference between English performance and Hindi performance, and comparing it to English Hindi performance, is still significant. So wrapping this part of the talk, the main contribution of this part of the thesis was a multi-domain cross-lingual data set, and I think also the pipeline that we used to create these candidates could be useful across different settings as well. You can apply it to a different task and probably reduce the time it takes to annotate or create samples in a different task as well. Coming to the limitations, if you remember the example that was shown, the ontology or the entities or the places that the data set is talking about is still Chinese, because that was a source data set that was being translated to other languages. So there is a certain improvement to be done there, where the ontology is replaced by more local, culturally relevant places or entities. The generation capabilities of these models was evaluated using BLUE. BLUE, as you all know, has certain limitations in monolingual settings itself, but more so in code mix settings. So they certainly, based on our qualitative analysis of the results, we felt that BLUE is underreporting as to how good or bad that dialogue agent was in code mix settings. Yeah, I'm going to rush through it. This is a second last component of the thesis, where we're trying to understand what are some of the methodologies that we can leverage for us to adapt a multilingual model to code mix settings. And the certain technique that we wanted to explore here was model merging. The key reason for this was because you have for a certain task, you might not have data in code mix settings, but you might have comparable data in monolingual settings, right? So how do you leverage this data? And we wanted to explore if model merging could be of help there. And the simple baselines that we were comparing it against was with the go-to approach generally is either fine-tune if you have data, or you can continue pre-train and then fine-tune. And we wanted to see if model merging provides any alternatives to this. Let me just directly skip to the results part of this. So the setting that is being discussed here is where you have in your particular language, you have unlabeled data as well as labeled task specific data, and you are not leveraging any task specific monolingual data, right? So in this setting, what these results essentially tell us is that model merging generally provides you incremental gains, very small but incremental gains over general methods like full fine tuning or continue pre-train and then fine tune. And these numbers were certainly better when you compare it with zero shot or few shot prompting of small or large language models. So we try to compare the performance against llama models ranging from 3B to 70B. But the key outcome here, or key takeaway here, is that these task-specific fine-tuned models were still giving you better performance than even larger models. The second setting that we wanted to explore was, can we add monolingual data, task-specific data into the mixture? For example, if you're doing the task of sentiment analysis, and you have sentiment analysis data for code mixed English Hindi, and you also have sentiment analysis data for English, can you add that to the data mixture and see if performance improves by any margin? So we added a few more baselines here, where we concatenated all the data sets and did a single fine-tuning run, or we fine-tuned one after another. We first fine-tune on English data, then fine-tune on English Hindi data. The main finding here is that when we added monolingual data into the mixture, the results performance gains were not significant, were not large. Even when we added all the data possible, the 3 data sources possible, they were not able to consistently beat continued pre-training by followed by fine tuning. I'll probably skip these slides. We can come back to this if there are any questions later. All right. So the last part of the thesis was to try to combine all of these components together into a single toolkit. So I have a small demo that I can present today. So again, these are some of the motivations that I have already outlined as to why we thought that this was a fruitful exercise, because again, lack of standardized pipelines across the research community, fragmentation of resources, where there is a large entry barrier as to how do you source these resources and put them together before you can actually ask questions of the data. So this is the basic outline, but let me quickly get into the demo. So I have basically a PyNB notebook, which is which a few examples that I want to showcase through this. The first thing that we wanted to standardize was what are all the metadata that is associated with a code mix sentence that is useful for you to analyze a code mix sentence, right? So we came up with this abstraction which has all the properties associated with the code mix sentence. That's what it looks like. What are your language tag set, English or Hindi? What are some of the other tag sets that you treat as non-language tokens, right? And this is a very important design point to remember, because if you do not have any other tag set, a token is either English or Hindi. What happens to named entities? Right? I'm going, मैं Hyderabad जा रहा हूँ. What is Hyderabad? Is it a Hindi token or an English token, right? So depending on what your tag set is, I mean, what any further analysis is contingent on that. All the code mix metrics that we discussed about in the previous whole slides, we provide an abstraction for you to compute it with a single function call. So all you need is the tokens, the associated language IDs, and all the associated POS tags, and you can just compute all the associated metrics with a simple function call. To basically to reduce the load on data access, we basically created a registry of all the data sets that we know of, not just from our work, but from previous work as well. And we provided means to list them out, see if there is any, if we can filter them out based on the task type, whether it is a sequence classification task or a token classification task or a sequence generation task. You can filter them out based on whether it is English Hindi or whether it is English Spanish. And so this data registry was basically a way to bring them to a single place, and again standardize all the metadata that is associated with that data set. While there were some other utilities, one utility that I want to showcase here is that we have also integrated some previously existing tools, some tools that we have found to be very useful. So this is an example of a LID tool, which would just take a sentence and would output these language IDs and the normalized form as well. So Hindi token, which was Romanized, it is converted back to its Devanagari form. And for each token, there is a language ID tag provided. So again, this was a tool that was previously existing, but we integrated so that we integrated and made a Docker image out of it, so that the access to that tool is much more easy than hard. Another component to this is standardizing the evaluation protocol itself. If you are using a large language model, you can get a data set and a model endpoint and get the performance metrics. So it comes with an associated prompt. For example, the example here on the screen is a hate speech classification data set that is there, and we are providing let's say a prompt bank where such prompts are already there. a model endpoint that you can hit and get these predictions. And you can apply this on, let's say, number of samples, and all the associated performance metrics would be there. The example is just there for 10 samples, but you can easily apply this to larger data set as well. A key thing to remember here is that the way that we have standardized the model part is using a utility called light LLM, and any endpoint that is usable through that library is usable here. But of course, the coverage probably we will have to increase going forward. This was a short demo of the toolkit. I'm happy to come back to it if there are any questions. But it also, before it can be released publicly and we can ask others to contribute to it, there are certain improvements that we have envisioned, and we will progress on this and probably share it with the larger research community in due time. Yeah, I think I'll skip to the final conclusion of the thesis. So in summary, these are the main components and the main contributions of the study. To start with, it was a metric called SIMCOM. Then the data set called CLINE, which is a human acceptability judgments on English in the code mix data. Then there's the dialogue data set that we had contributed. And we looked at some model merging techniques, which would give you better performance as compared to the existing approaches. And the final component of the thesis was a code mix toolkit, which sort of brings necessary components together. In terms of broader impact, I think the key gap that this kind of work fills is that it doesn't enforce on a user a particular way of language use. It allows users to talk how they normally talk, and you want to enable language technologies to be able to deal with such diverse patterns of language use. And we also the human acceptability part of it. We had a data set where human perception of code mix data is front and center of the whole work. In terms of societal applications, I think code mixing as a tool or as a device can be very important when you are trying to educate people. You're trying to talk to bilinguals in a much more comfortable format, and when you are dispensing digital goods to people, this could be a very useful device in that effort. And in social, we have already discussed the social media part, especially if you have to govern a social media space or moderate a space. Having to cover such kind of diverse language uses is also very important. In terms of limitations, one of the key limitations of the study is this focus only limited to English Hindi. Coverage to more language pairs is always necessary, but also equally challenging. Having created a couple of data sets, there is still a large gap in evaluation benchmarks. Unfortunately, the code mixing evaluation landscape is still limited to sentence classification tasks, tasks which are slightly lower in the NLU ladder. We have to climb up in that space. Our investigation into resource efficiency, let it be sample or compute efficiency, has been limited, but that is definitely a fruitful avenue for further research. Yeah, that is essentially what I have presented here. But I think I am at the end of the talk, overrun by 15 minutes. But let me take a moment to thank people who have been central to this thesis. I mean, 45 minutes, 6 years of work does not happen just by an individual. There is like you need a village to raise a child. There was a village to raise this thesis. First of all, I think I should thank Microsoft Research India for the PhD award. It came at a very crucial stage. It was a last 2 years of the PhD work, and this was certainly a motivation, if not anything else. To all the co-authors, there are around 5 papers that I presented in this work. It couldn't have been possible just by some individual's effort. So there have been master students, there have been dual degree students, single degree students who have helped out a lot. with their time, their brain share, and their energy into the work. And they also keep you young. So that is always a plus. To all the fellow researchers, I had a privilege because I was co-advised, I had views into two different labs, how two different labs functioned, and I had my cohort was pretty large, right? I had PhD students in one lab, I had PhD students in another lab, and to learn from those experiences is always the fun part. You're as good as your cohort, and they always help you raise your standards. All the staff of IIITH, especially we had to we throughout these 6 years we interacted a lot with LTRC staff or PG cell, and they basically provide the whole ecosystem in which we can flourish, we can thrive. So thank you for them. I think Professor Monojit, I mean, I don't know what to call him. He has been a mentor, he has been a collaborator, he has been just a wonderful person to interact with and learn from. And he has been very generous with his time, right? Because I have started interacting with him from 2021 onwards, and he has been a constant source of push, encouragement, and guidance. And to the two advisors that are there in the room, starting at 2019, I think it was a time where I had no research experience to start with, and these two gentlemen thought it is worthwhile to take a risk on a profile like me. So for that, I thank you. And I also, I mean, anything that I do from here on, however the research career pans out, the whole credits of it should probably go down to the contribution of these two gentlemen. Finally, to my parents, their support has been unconditional. Everybody has these stories right around the time they have come. I think I should thank them. Their support has been unconditional. Everybody has these stories where you have board exams and your parents are up with you at around 5 a.m. in the morning. And they have done that essentially when I'm 30-year-old as well. Finally, to my wife, Pravalika, she's here at the very right moment. To undertake a PhD journey when you're 28 years old, 8 months into a wedding, is quite an undertaking, right? And there has never been a second thought. It would have been at my end, but not at her end, certainly. And throughout these last 6 years, which has been rather long journey, one could say, there have been no ifs and buts. My parents and my wife, their support has been, unwavering and continuous. With that, I would like to end. I've extended beyond 15 minutes, but thank you so much for your patient ears, and I'm happy to take any questions if there are. Time will tell.
Quick